In lesson 12.4, you will find sums of infinite geometric series. Remember from section 3, a special sequence was called a geometric sequence, and it had a geometric series or sum. A finite geometric series can be found using this formula. The sum S sub n of the first n terms of an infinite series is called a partial sum. And in example 1, we're given an infinite geometric series. We want to find and graph the partial sums S sub n for n equals 1, 2, 3, 4, and 5. Then describe what happens to S sub n as n increases. So S sub 1 is going to equal that first term 2. S sub 2 is the sum of the first two terms. So 2 plus 2/3 or 6/3 plus 2/3. Getting a common denominator, which is a total of 8/3. S sub 3 is the sum of the first three terms, so 8/3 plus 2/9 or 24/9 plus 2/9, which is a total of 26/9. S sub 4 is the sum of the first four terms, so that's going to be 26/9 plus 2/27 or 78/27 plus 2/27, a total of 80/27. S sub 5 is the sum of the first five terms, so that's 80/27 plus 2/81 or 240/81 plus 2/81, which is a total of 242/81. Now the ordered pairs that we're going to graph look like this. When n is 1, our sum is 2. So we'll graph 1, 2. When n is 2, our sum is 8/3 or 2 and 2/3. 2, 2 and 2/3. Okay, then when n is 3, our sum is 26/9 or 2 and 8/9. 3, 2 and 8/9. Okay, when n is 4, our sum is 80/27 or 2 and 26/27. See the pattern? 4, 2 and 26/27. So we're getting infinitely close to a horizontal line that crosses the y-axis at 3 with these ordered pairs. When n is 5, 242/81 can be written as 2 and 80/81. 5, 80/81. So again, it says, then describe what happens to S sub n as n increases. S sub n approaches 3. Our sums approach 3 or get infinitely close to 3. An infinite geometric series is the expression formed by adding the terms of an infinite geometric sequence with absolute value of r less than 1. So here's our formula for that sum of the infinite geometric sequence. In example 2, we want to find the sum of the infinite geometric series if it exists. So we have to test to see if it exists. Our common ratio in our first problem is 1/10. And since the absolute value of 1/10 is less than 1, we can find a sum for this infinite geometric series. All we have to do is use our formula. So we need the first term, which is right here, 2 over 1 minus that common ratio of 1/10. And simplifying, we have 2 over 10/10 take away 1/10 is 9/10. And inverting that denominator and multiplying it to the numerator, we get a product here of 20/9. So the sum of this first infinite geometric series is 20/9. Now in the second geometric series, we'll find that common ratio by dividing. 4 divided by negative 12 is going to give us a common ratio of negative 1/3, and since the absolute value of negative 1/3 is less than 1, this infinite geometric series is also going to have a sum. So we need the first term divided by 1 minus that common ratio of negative 1/3. So we have negative 12 over 3/3 plus 1/3, which is 4/3. And again, we'll invert and multiply. And we'll be able to cancel a factor of 4 top and bottom. So we get negative 3 times 3, or a sum of negative 9. Negative 9 is the sum of this second infinite geometric series. Okay, now looking for a common ratio in our third problem, we divide. 3/2 divided by 1 gives us a common ratio of 3/2, but since the absolute value of 3/2 is greater than 1, there's no sum that can be found for this infinite geometric series. In example 3, a rubber ball is dropped from a height of 60 feet. Each bounce takes it to 2/3 of its previous height. What is the total vertical distance the ball travels? So let's draw a picture of this ball that's dropping and then rebounding 2/3 of its previous height. In theory, this ball should never stop, but we know that gravity and friction is going to eventually bring it to a stop. Well, we can find the distance that that ball has traveled by considering two infinite geometric series. Let's first find the distance that it falls. This ball falls or drops. It first falls 60 feet, and then it's going to fall 2/3 of 60, and then it's going to fall 2/3 of 2/3 of 60, and then it's going to fall 2/3 of 2/3 of 2/3 of 60, and this pattern is going to continue on and on forever in theory. Now this can be written as the sum as I goes from 1 to infinity of a first term of 60 and a common ratio. There's a new factor of 2/3 in each term raised to the I minus 1 power. Now since that common ratio of 2/3 is less than 1, the absolute value of it is less than 1, we can find its sum using our formula. It's the first term over 1 minus that common ratio. So it's 60 over 3/3, take away 2/3, 1/3. And inverting and multiplying, we have 3 times 60, or a total distance that this ball fell of 180 feet. Now let's consider the rise that this ball makes when it rebounds. Let's consider that vertical distance. So it's going to be rising first 2/3 of 60, and then it's going to rise 2/3 of 2/3 of 60, and then it'll rise 2/3 of 2/3 of 2/3 of 60. And again, we have a pattern that continues forever in theory. So this can be written as the sum as I goes from 1 to infinity of a first term of 2/3 of 60, which is 40, times that common ratio, again that new factor in each term of 2/3 raised to the I minus 1 power. So again, it has a finite sum for this infinite geometric series. The first term is 40, and that's over 1 minus 2/3. So it's 40 over 1/3. And inverting and multiplying, we have 40 times 3, which is 120. So altogether, this ball travels a vertical distance of 180 plus 120, or 300 feet. In example 4, we want to write the repeating decimal as an infinite geometric series, then write it as a fraction in simplest form. So expanding, I'm first going to write this repeating decimal as 0.51 plus 0.0051 plus 0.000051, and that'll continue. So I can write it as 51 times 0.01 plus 51 times 0.01 raised to the second power plus 51 times 0.01 raised to the third power, and so on, which means this is the sum as I goes from 1 to infinity of a first term of 0.51 times a common ratio of 0.01 raised to the I minus 1 power. Now this has a sum because the absolute value of that common ratio, 0.01, is less than 1. So I'll take the first term, which is 0.51, and divide it by 1 minus that common ratio of 0.01. So we get 0.51 over 0.99, and I'll multiply top and bottom by 100 to get rid of those decimals. So I have 51 over 99, but there's a factor of 3 in common top and bottom. So getting rid of that factor of 3, I can simplify this fraction to 17/33. Now this is the sum of that infinite geometric series, but it's also the fraction that's equivalent to the repeating decimal 0.51. Okay, let's try it again in this second problem. Let's write it as 5 plus 0.146 plus 0.000146 plus 0.000000146, and on and on. Okay, so I can write it as 5 plus 146 times 0.001 plus 146 times 0.001 raised to the second power plus 146 times 0.001 raised to the third power, and so on. Okay, and now I can write it using sigma notation as 5 plus the sum as I goes from 1 to infinity of a first term of 0.146 times a common ratio of 0.001 raised to the I minus 1 power. Okay, now because the absolute value of 0.001 is less than 1, we can find that sum using our formula again. So we have the first term, which is, we have 5 plus the first term, which is 0.5146 over 1 minus that common ratio of 0.001. So that's 5 plus 0.146 over 0.999. And I want to get rid of those decimals again by multiplying top and bottom of this fraction by 1,000. So I have 5 plus 146 over 999. And now I need a common denominator so that I can combine these two terms. So I'll write 5 as 4,995 over 999, and add that to the 146 999s that we have. So we're going to get a total and a fraction of 5,141 over 999. So this fraction is equivalent to that repeating decimal 5.146, 146 repeating.